your work energy test either Wednesday or Thursday, depending on who I teach, what block you're in. Key concepts. So first of all, you need to know the 3 definitions of work. Once again, you can write this down or I can print this up for you, whichever way you think you'll learn better. And again, I'll post this online too. 3 definitions of work. Now, what are they? The first one was work equals force times distance. The units, joules. And I guess a joule is a Newton meter, technically, if I look at force times distance. And this is really important. It's a scalar. It's a scalar. The last thing was F and D must be in the same what? Direction. If not, components. But you know what? I think I flogged components to death last test. And we had another definition of work. Oh, I didn't want to do that. I want to go like that. Work equals now let's see if I can cleverly go like this. Click, right click. Will you let me go table? Will you let me go combine row? You know what? Let's go like this. Click. Table. Trying something new out. Show me a delete cell. Oh, heck. Work equals the area under a force versus distance graph. Let's paste that right there. You're absolutely going to have a written question where I give you an area, and I'll tell you right now, it won't be a rectangle. It'll be a triangle or a trapezoid.
Good afternoon, everybody. Just a reminder to our department heads, we do have a meeting today at 3:15, just over 10 minutes from now. If you're still here, that meeting is off-site.
The third definition of work.
Thank you.
Work equals what? So this is the what we call the work energy theorem, and this was what related work and energy together in one equation, and I'm not sure I can actually type this. I think I'm going to have to hand write it unless I can find a delta symbol. Insert equation, sure. Insert a new equation. Hey. W equals, where's my equation menu? Equation tools. Where's my delta? I haven't tried any of this. Sorry, you guys are my guinea pigs here. Symbols, show me more. Haha, delta KE plus delta PE. This was the work energy theorem. Can I go a little bit more, Mr. Dueck? Hey, there we go. That kind of fits on one screen. These are the 3 definitions of work. Probably you can expect some combination of the area and this one, or this and this. In other words, I may give you an area under a graph and say, how fast is a car going? Or how fast is an object traveling? Well, you actually, if you know the work, you know the change in kinetic energy. Or I may give you the area under a graph and say, if the average force on a spring was 2 newtons, how far did it travel? Well, if I gave you the area, I gave you the force times distance. If you know the force, you should be able to get the distance. Or, in other words, If you know this, you know the left-hand side, the number that goes where the W is, and I can ask you to find something on the right-hand side of the first two definitions. I'll see if I can find an example of one in a little bit as well. Okay? Then we talked about energy. We said it was the ability to do work. And we broke things up into two main types. And this is where I think I'm going to stop typing for a while. We talked about kinetic energy. And we talked about gravitational potential energy, which we just abbreviated as potential energy, and it was mgh. This brought us to the law of conservation of energy. What did that say? It said kinetic energy initial. Oh, are you really going to do that? Okay, click. Stop automatically correcting that. Plus potential energy initial. It's going to have fun with that because it's going to think it's Prince Edward Island. Stop automatically correcting that. Equals, and let's go make them subscripts. I'd probably handwrite this faster, but not neater. Kinetic energy final plus potential energy final. Subscript, subscript. And then we also said, if necessary, plus heat if friction is mentioned. Where do we use this? Is there a change in height, speed, and curvy path? I'm not sure if that's how you spell curvy, but it is now. Okay? Then we're going to use conservation of energy. Let me show you some examples here. I've dug up the old work energy review that I used to give out to my students back when I physically cut and pasted actual provincial exams and glued them to a piece of paper. Yes, cut and paste used to actually mean cut and paste as opposed to what it does now. So let me see if I can scan a quick one. Well, even something like this. So number 6 says, this is a conceptual question. Child's ball rolls up a hill as shown. The same child then throws an identical ball up the hill. When both balls end up in the same location, which correctly describes the change in potential energy? What do you think the correct answer is here? A, both balls have the same potential energy change. B, there is no potential energy change for either ball. C, the thrown ball has greater, or the thrown ball has smaller. What do you think, Michael? A. Why A? You're right.
It shows the final and initial positions.
Okay, so we said change in potential, final minus initial. Potential is just mgh. And the nice thing about energy, it doesn't care about the path you took to get there. Now, at one point, the thrown ball at the top would have had more potential energy, but you know what? It lost it. Okay. Let me see if I can find an actual question. We're going to crunch some numbers. Remind me to come back to number 10. That's a nice example of combining energy and work together. What I'm really looking for is, something like this. Okay, can I make this a little bit smaller, Mr. D? There we go. That's a little bit too small. How about 125? So here is a curvy path. Let me copy this. Is this a roller coaster? Say yes. Then you know what? The odds are I like this question. You're definitely going to get, this is such, first of all, a great example of conservation of energy, and it's an amusement park ride. How can you're going to have a roller coaster question on your test, okay? What will I ask? I'll either ask you how fast it's going at the bottom, or I'll tell you how fast it's going and say how high did it start, or I'll tell you how fast it's going and how high it started, but I'll say how much did it lose to heat, because the numbers won't add up otherwise. In this one here, it's wanting the speed at the bottom. Is there a change in height? Is there a change in speed? Why, we would say something like this. Kinetic, good gosh, come on, pen, right. Come on, pen. Kinetic, initial, potential, initial, kinetic, final, potential, final, and heat. Why heat? Because they're mentioning heat. Yes, but sadly nothing else. Make sure you read the question carefully. Sometimes you would start at rest and you could cross out kinetic initial, but sometimes not, so don't get cancel loopy. It's going to be, what does it want me to find? It's going to be a half mv initial squared plus mgh initial minus heat equals a half mv final squared. Did I do too much, Peter, or was that okay? I did 2 steps at once. I substituted the actual formulas in, and I got kinetic energy final by itself because I said they want me to find V final. Is that okay, Neve? How would I get V final by itself? Bree, I think you're right. How? Divide by a 0.5, divide by an m. M's don't cancel this time because sadly there's no mass and heat. And then how to get rid of the squared? Yeah, this I'd probably do in separate steps because it's a lot to type in one fell swoop. I'll write it. I'll say, okay, divide by 0.5 m, and I would go yoink. Cross that out, so I would say, okay, there's my equation. That's a, you know what? I'll type everything into the square root, press equals, and then I'll square root that. I'm pretty sure Jacob will have this. V final is going to be the square root of 0.5. Says the mass is 250. Says the speed is 12 squared plus 250. 9.8, 18, minus heat, all divided by 0.5 times 250. Am I wrong? I heard somebody whispering. Did I make a mistake? No, I'm good. Holy smokes. Because I've been terrible today. A half mv squared plus mgh minus 8,500. Double check my typing. Yes. Divided by bracket 0.5 times 250. Square root. And I get, I hope, 20.7. I hope that's right. I knew this. How fast was I going at the top of the hill, Ryan? Am I going to be going faster or slower at the bottom of the hill? In other words, if I got an answer less than 12, I know I screwed up, right? There's some built-in error checks. Not going to get a negative answer. This idea, though, this notion of conservation of energy, we're going to be using that, Josh, a lot more this year. Because when we look at electricity, we're going to say, oh, I'm going to show you what electric potential energy looks like. And we're going to have also, oh, and I'm going to show you how you find another way to describe electric potential energy in terms of speed and voltage. So we're going to modify this, but this is going to, it's a flexible equation. Is that all right? I said that you want to be able to handle a combined question. So let me see if I can find, I'm going to see if there's a good graph question. Otherwise, Ugh. Some of these also appeared on your review. So let's try number 10. That looked good, I think. Oh, you know what? This is a momentum question. Ha! That's why I didn't assign it. It's a combined energy momentum question. Do you know how I know this is a momentum question? Because when you cut when you cut the string and the spring goes doing, isn't that actually an explosion? See, I could glance at that and say, I bet you that's a job for conservation of momentum. Now they're asking how much work. Probably what I'll do once I find all the speeds, all the velocities, I could probably find out how much kinetic there was initial, how much kinetic there was final, and work would be change in kinetic plus change in potential, and I could find how much work. Let me find from here a good one and just change the numbers. Sure, let's do this. The graph below shows, I'm going to change the mass. What did I say? 3.5 kilograms in the original? 5.0 kilogram. Actually, let's have it go faster. Let's make it 1.5 kilogram object. Copy the graph. Yoink. Okay. Little big, Mr. Dueck. Yoink. You guys can see the numbers, I think. If friction is 0, if no friction, and we start at rest, find the final speed. Say what? First of all, what kind of a graph is this? What versus what? Well, I think that's work. I think I would say, and what do they want me to find? A speed. I didn't put a vector on there on purpose. That is a speed. You know what? I would say work equals change in potential plus change in kinetic, where W is going to be the area underneath this graph. And I would also, I think in the question, it implies it's a horizontal surface in the original. Yeah, it does say horizontal surface, so no change in potential. What is the area? What shape is triangle? What's the area of a triangle? You know, the number of kids that go like this, oh, it's going to be 8 times 16. That's the area. Drives me crazy. That's the area of a rectangle. What's the area of a triangle? It's base times height, what? In fact, I think I end up with 64 joules of work that have been done on this object. And if there's no friction, that energy had to go somewhere. Must have gone into kinetic because there's no friction. So what I'm really then saying here is this. 64 equals a half mv final squared minus a half mv initial squared, yoink, because at rest. I think what I'm really saying here is V final is going to be 2 times 64 divided by 1.5. Is that right? Times by 2, divide by the mass. Oh, and then square root. Boy, if I'd been really clever, I would have let the mass be 2, because then the 2 on the bottom would cancel the 2 on the top, and I have the square root of 64, and it would have worked out evenly. And how often does that happen with me? Like, never. But anyways. Is this right, Jordan? Yeah, I did the math correctly, I think. People are not arguing, so okay. Oh, square root, Mr. Dueck. It's going, that seems really fast. 9.2 meters per second. So that would be an idea of a combining two definitions of work question. Okay. Hey, what else could I have asked? Oh, I could tell you how much heat we lost and then say how fast. So how much work was done? How much work was done? 64 joules. What if I told you we lost 10 joules to heat? How much work would I have left for kinetic energy? 54. Or I could give you this graph, tell you how fast, and supposing I said the final speed was only 8, you'd go a half mv squared and you'd say, wait a minute, I did 64 but joules of work, but if the final speed was 8, you'd go a half times m times 8 squared, and you'd say, I only got 48 joules of work in the object. You know what? I must have lost that much to heat. I could say, find the heat. That would be a nice little curveball. Oh, and now that I know the heat, what distance did we move it for? In this graph, what distance did we move it for? What distance did we move it for? 8 meters. Hey, if I knew the heat, if that 16 was the heat, I could now say force times distance, force times 8. I could find the average force of friction, in theory. Okay. Just trying to think of ways I can mix and match. I'd consider that last one, by the way, a nasty part C. I'd probably make it worth like 1 mark or 2 marks. But I could. Okay. So there is going to be some kind of use the graph, do something with it, combine it with work and energy and stuff. If you're looking for more examples like that, so in your review 10, certainly number 12 is another good example of that. 14 is a little curveball where I'm going to have to use my understanding of graphs, because on the y-axis I have work, on the x-axis I have distance. This is a guess. I haven't even scrolled to part B. Is part B asking you about the slope? Yes? And that would be work divided by distance. I think that's force, because as if work is force times distance, if I write work, I bet you the slope is the average force. I haven't even looked yet. Slope of the, oh, what does the slope of the line represent? I bet you it's going to be average force, because it's going to be Newton meters per, it's joules per meter, it's force. Oh, here's another good example, number 15. This is a nice combined question. So they're giving you the force required to compress the spring. Is the force constant? Is the force constant? No. If the force was constant, it would always be 20 high. Is the force constant? No, it's changing, which if you ever compress a string, you may have noticed it's easy to compress at the beginning, but the further you go, the harder you have to push. So if I wanted to figure out how much energy was stored, it would be the work, it would be the area underneath this graph here. Okay? So what's the work done? Area. What's the maximum speed? Work equals change in potential. Oh, if I tell you the maximum kinetic energy is that, what's the efficiency? So that would be a nice little written question as well. Good ways that we can combine work, energy, and heat. Okay? So you can definitely expect a roller coaster question. You can definitely expect, I would have called this combining the 3 work definitions and applying it to something. We've done power. We said that power was what? It's the rate at which work is done. Measured in what? 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 Oh, oh. Yeah, watts. Okay. Power, scalar or vector? How do you know? Because what was the equation for power? Hey, I think I can enter that. Woohoo! Insert equation. Equation tools. Where's my fraction thing? Power equals work over time. Work, scalar or vector? Scalar, time, scalar or vector? So what do you think a scalar divided by a scalar results in? A scalar. Okay, so power, scalar, measured in watts. Or, remember we had this obscure one that showed up every so often as well. It was also, actually I can just write it. It was force, average force, times speed. Because that actually popped out of the work over time. There will be a few questions on power. I'll be honest, we're really going to hit power with a vengeance when we do electricity, because we'll find out how you measure electric power, which is also measured in watts. But the written section, I'm telling you, it's going to be some kind of an applied work combined question, and then 2 or 3 conservation of energy questions. So having said that, any questions from the review that you would like me to go over, stuff you're wondering about? That you're going, holy schmoly, Mr. Dueck, I have no idea how the heck to get that. Let me just see if I've kind of covered what I wanted to cover. Yeah, sure. There's going to be 1 or 2 using principles of physics right to explain questions. One of them almost all of you should get, because I've gone on a rant about it numerous times. The other one, I went on a little mini rant at one point, and hopefully you picked up on it.
Can you do 39?
Sure'd like to. That's like towards the end. Is that scholarship?
No, it's not.
Oh, by the way, which one did you ask me earlier, Callum?
Oh, is that?
Oh, here. 38. So I pulled these from old provincials, and this question was in the work energy section of the provincial, and I think you could solve this with work and energy. I solved it with forces. So if you're wondering about 38, I went winner minus, I drew a free body, I went winner minus loser, because they said, what height? I said, oh, why don't I find the distance, and then I can just do some trig and find the height. In fact, I'm pretty sure I gave you this question on your last test, in that there was a question with the ramp where I said find the distance. I just didn't go one step further and say, oh, tell me how high it is if you know theta. But so 39, Callum?
Yeah.
Oh, very convenient. Okay. Probably not going to give you one quite this. Maybe I might feel comfortable as a multiple choice, not as a written. I'm not going to give you components as a written. Okay. It's a lawnmower question, so I broke it up into components. You'll notice I wrote down here, hey, work and distance must be in the same direction. It says how much work was done by the applied force. It's going to be Fx times distance, which is going to be 1,000 times cos times distance. That's how much work was done by the applied force. Now, that doesn't mean that all of it went into the block. So I got 2 times 10 to the 4th, what's that, 20,000 joules? Is that right? Yeah, I got 20,000 joules, but apparently I would have lost whatever 300 times 25 joules of heat is, because if the friction force is 300 times 25, is that okay? Yeah. And the rest of it would have gone into, this would be, I could have given you this as a nasty written, where I could have given you this, all this diagram, and said, how fast is it moving if we start from rest? You would say, well, that's how much energy I put in, 20,000. How much did I lose? Force times distance. What's left? That's the kinetic energy that went in speeding the block. Now go make that equal to a half mv squared times by 2, divide by the mass, square root, and you got your speed. That would be overkill. Cool, though, but overkill. I'm thinking I may turn this into a quiz question next year, because I want my quizzes to be a little nastier. Is that all right?
Yeah.
Note to self, remember number 39, steal that diagram, change the question. Any others? Number 17, was that the one that I said was crazy nasty? There is one here that's a real... Is 17 the... Oh, no, 18 is the one. 17. 17, I was trying to think of a nice way to write this mathematically, and I just couldn't quite see it. So here's what I wrote. I said, look, as far as I can tell, all of his gravitational gets stored in potential when he lands. All his gravitational potential gets stored on the trampoline. So I was going, it's kind of potential becomes potential. You know what I said? I said all of his gravitational potential energy, which is that, is going to get stored in the trampoline. And it would then turn into kinetic, and I could do something with it. I didn't want to call it potential. It is stored energy in the trampoline, which is also potential. I was just worried I'd have a PE and a PE that were different that would confuse the heck out of me. I guess I could have called it PE tramp or something like that. I don't know. Is that okay? I said he's initially got MGH, and he finishes with, oh, not 10, 9. Why? I let the ground be right here because I could. Why not? Is that okay? Any others? Yep.
Can you please go over 18?
Yep. Number 18, I'm going to ask, did anybody, without looking at my answer key, get number 18 on their own? Nice. Nice. This is tough. Okay? So here's my argument. And I'm going to start out here and then scroll down. What do they want me to find? dx, how far away? So I wrote down here, well, I know that dx equals vxt. What happened to a half at squared horizontally? No acceleration. Okay, you ready?
Yes.
You back?
Yes.
Okay, look behind you. There's an attention span. You might want to grab it. And okay, here we go. Ready?
I'll just read the question.
What's this question asking me to find? How far away will it? I said, you know what? That's a dx, a horizontal distance. So I wrote, honestly, when I first saw this, first thing I wrote, If you ever see me write that, what that means is I had to pause, put my pencil down, and think for a while. That means it's a nerdily cool question as far as I'm concerned. I have a love for those, but I was, okay. So, I said, well, I know this. I also said time is going to be based on how far it drops, and that's not changing. It's dropping this far. No matter how fast you're traveling horizontally, vertically you're falling the same height. Vertically you're traveling the same time. Horizontally, that means you're traveling the same time. So I wrote down, really what this is going to depend on is my horizontal velocity, because time's not changing. You okay with that, right? Okay. Is there a change in height? Is there a change in speed? Is there a curvy path? I said, well, so I wrote this, and I said, all right, let's get the V by itself, and let's really analyze it. I said, this is V final right now from a height of h. What if I double the height? Now, if I double the height, instead of an h, you know what I'll have right there? A 2h. Like that. And I said, really, what that means is, if you look at my original V final, what's inside the square root? A 2? And? If I double the height, do I still have a 2 there? Do I still have a g there? Do I still have an h? You know what? I have an extra root 2 kicking around. So I already kind of started to lean towards this one, just because of that. I said, you know, if I double the height, I don't go twice as fast, Michael. Turns out, for slides, if you build the slide twice as high, you only go root 2 as fast. In other words, if you build the slide 4 times as high, you're only going to go twice as fast at the bottom. If you build it 9 times as high, you're only going to be going 3 times as fast at the bottom. This is why, by the way, it's really not that worth it to build big, huge, high slides. Even if you've ever done Playland, used to have the big, huge slide. You really can't go and you don't go really, really fast, despite the fact that it's all that much higher. Okay. Also, there's lots of friction on that slide for safety reasons as well, but still. So I said the difference is this, which means that normally There's my range. If I double the height, all I'm going to end up with is an extra root 2 there. I said doubling the height increases v final by a factor of root 2. And so, Jacob, that's going to increase the range by a factor of root 2. There's another way you could have done this. You could have made up reasonable numbers. I did this algebraically. You could have said h height 10. What would 2h be then? 20. You could have said, oh, and I'll make this like 1 meter high or 2 meters high so I can find t, so I can actually crunch the numbers and I can tell you how far it's going to travel horizontally. And then I could tell you, if you double the height, how far it's going to travel horizontally. And then if I just divide those answers, either I'm going to get a 4 or a 2 or the same answer or a weird decimal that's really close to the square root of 2. Would I expect most of my kids to get this one? No. Would I expect almost all my kids to have just followed my explanation? I hope so. And for those of you that are here, I almost guarantee that someone's going to ask me this question when I have that little 10-minute tutorial at the beginning of that someone else is going to ask and say, I couldn't figure that one out, because they just started doing the homework tonight. Is that okay? Any others? Yeah. Number 19. Cool. So it says energy versus time. By the way, as soon as I saw that, I said, do I have an equation that has energy and time in it? Well, I do if I think work and time. There is an equation that has work and time. Power. Okay, so right away I started thinking, because we're analyzing a graph, power. Oh, and in fact, I think power is going to be, power is work divided by time. The slope of this is going to be the power, I think. Let's find out. I kept reading. Oh, find the power output of the bulb. And I said, well, power is work over time, which really is energy because it's in joules over time. It's the slope of the graph because it's rise over run. So I went rise over run. I kind of eyeballed it. I said, well, that's definitely a run of 7. And I said, this looks about halfway between 48 and 56. So I went 52 over 7. I said, it's around 7.4. And marking this, we would have taken anything between like 7.3 and 7.5 watts. It's about a 7.5 watt bulb, give or take. Is that okay so far, Sally? Then it says, if it's 20% efficient, find the power delivered to the bulb. I said, okay. Efficiency is out divided by how much you get divided by how much you put in. They told me the efficiency 20% or as a decimal point 2. And I'm getting out 7.4. What am I putting in? I solved for that. So I cross-multiplied and I got 37 watts. Okay. You know what? This bulb is actually probably a 40-watt light bulb. We're getting 7.5 watts of light. Where's the rest of the power going? Heat, which is why it's 20% efficient. And I went on my rant how actually that's not efficient because that heats up our houses in the winter and we're not actually losing that. Okay, I did do that. Good. I mean, I'm all for environmental and let's be good, but that's one I think they've really goofed on. Is that okay? Next. Do you have your reviews here? Good. I like number 2. I like number 2. I like number 2. I like number 4. I like number 6. I like number 7. I like number 9 in that there's another example of combining an area and some kind of applied work question. And it's a little curveball saying, oh, find the mass. Oh, okay, instead of the speed. Oh, because I guess you know V initial and it's stopping, so you know V final, so you know both the speeds, so you know the change. And anyways, again, hopefully you picked up my hint. You're going to see something like this on the written, right? Yeah, 10 is good. I like number 10. I like number 10. I like number 10. I like number, again, you need to understand number 12. From 20, oh, got to be a little careful because it's going from 20 meters to 60 meters. So it's this area here, which is a rectangle. It's a trapezoid and a triangle. Definitely like number 13. Oh, you know what? Looks like number 13 is exactly the same as the one that I did from number 10 from the old provincial, because even the numbers look identical, aren't they? Whoops. I like number 15. I like number 20. I like number 20. I like number 20. Now, in number 20, okay, again, with something like this, to me, there's several options. I can tell you how much heat and say, hey, find the final speed. Or I can tell you the final speed and say, hey, how much was left over for heat? How much work did friction do? If I did that and it was a straight ramp and you knew the distance, remember, if you know the work done by friction, if you know heat, that's force of friction times distance. You can actually find force of friction. I think on one of my versions of a test, there's a multiple choice that has that as a little curveball, I think. Oh, okay, I was looking, going. Oh, you know what? Like 22. So 22 part A, how much energy is transformed to heat? That's straight conservation of energy. But once you know the heat, part B says, what's the average force of friction? Well, heat is force of friction times the distance of the ramp. Oh, so that's why they told me how long the ramp was. As a matter of fact, if they'd given me the angle, they didn't need to tell me how long the ramp was. If they told me the height, I could have done the trig and found the length of the ramp. I could have done Pythagoras and SOHCAHTOA. So I like number 22. I like number 22. I like number 22. I like number 27. Sure, something like, well, no, 32. Yes, except all it's asking for is the work, and I've told you I'll ask you to do something. I'll ask you to do some work with the work. Okay, fine. I like number 35. See, I would argue 41 is tough-ish, but not that bad for a scholarship. I'm not saying I like it, but there is one on here that I think I do like. No, that's a little over. Oh, no, I'm getting this mixed up with a different one. I thought there was one scholarship that I did like, but I think we're good. So there's some hints. Okay. So let me pause the video.